In this lecture, we are going to discuss the use of the moment area method for calculating slope and deflection in beams. Let's start by considering a cantilever beam subjected to a concentrated moment at its free end. The length of the beam is 4 meters. Naturally, the beam is going to deflect upward like this. We refer to the deformed line along the neutral axis of the beam as its elastic curve. Let's use theta A to denote the slope of the elastic curve at the left end of the beam, and use theta B to refer to the slope at the free end. According to the moment area method, the difference between the two slopes is equal to the area under the moment over EI diagram between the 2 points. This is called the first moment area theorem. Please keep in mind, although we are referring to points A and B here, the theorem works for any pair of points on the beam. Let us see why this relationship holds true. In lecture SA22, we showed that for an infinitesimal slice of a beam, the difference between the slopes of the elastic curve at the ends of the slice can be expressed in terms of the internal bending moment at that point. More precisely, we can write, here we are assuming that the beam has a constant, EI. Integrating both sides of the equation over a specific interval, say from point I to point J, along the length of the beam, we get the left side of the equation equals, and the right side of the equation is equal to the area under the moment over EI diagram between the 2 points. If we apply this expression to segment AB of our cantilever beam, we get. Now that we know the basis for the theorem, let's use it to calculate the end rotations for the beam. The moment over EI diagram for the cantilever beam is Therefore, our equation can be written as where 12 over EI is the area under the M over EI diagram between A and B. And since theta A is 0, the equation gives us theta B. Let's consider another example. Suppose we wish to determine the slope of the elastic curve at the midpoint of the cantilever beam. Since we know theta A, we can write the area under the M over EI diagram for the beam segment between 0 and 2 is 6 over EI. Therefore, we can write, or now consider a simply supported beam subjected to a concentrated load at its midpoint. Suppose we wish to determine the slopes of the elastic curve at the ends of the beam. Let's draw the beam's M over EI diagram and its elastic curve. If we label the end rotations as theta A and theta B, knowing that the area under the M over EI diagram is 18 over EI, then according to the first moment area theorem, we can write. Here, however, neither theta A nor theta B can be calculated, since we have one equation with 2 unknowns. To be able to use the first moment area theorem, we need to know one of the slopes in order to determine the other one. For our simply supported beam, given the symmetrical nature of the load, we know the slope of the elastic curve at point C, where deflection reaches its maximum value. That slope is 0. Therefore, we can write, or, as we just saw, the first moment area theorem has limited computational use. The theorem can be used to calculate the slope of the elastic curve at a point only if we already know the slope at another point. For example, consider the same simply supported beam, but with an off-center load. Here, the maximum deflection occurs somewhere between points C and D. Since we don't know the exact location at which slope of the elastic curve vanishes, the first moment area method cannot be used to determine the end slopes. For that, we need to utilize the second moment area theorem. What is the second moment area theorem? Consider the simply supported beam with the off-center load. Here is its M over EI diagram and elastic curve. In essence, the second moment area theorem states that the vertical distance between the tangent lines at A and B, measured at B, is equal to the moment of the M over EI diagram about B. That is, distance, delta BA, can be computed by taking the moment of the M over EI diagram about point B. If we view the moment diagram consisting of two right triangles, we can easily calculate each area. And multiply it by the distance from its center to point B. Then, adding the two terms gives us the moment of the entire M over EI diagram about B. Further, since beam rotations are assumed to be small, we can write theta A equals tangent theta A equals delta BA divided by 6. Or, please keep in mind that this is a negative slope, so in a strict sense, we should write. Now that we know how the second moment area theorem works, let us see why the theorem holds true. Consider an infinitesimal element in our cantilever beam. The element carries an internal bending moment of m, which is causing the differential end slope, d theta. The mathematical relationship between m and d theta is, without loss of generality, let us assume the element is located at distance x star from the free end of the beam. Multiplying both sides of this equation by x star, we get. Note that the left side of the equation equals the vertical distance between the two end tangents at distance x star from the element. If we integrate x star d theta from A to B, we get the total vertical distance at B between the two tangent lines. So, we can write, now that we know the geometric interpretation of the left side of the equation, let's turn our attention to its right side. This term represents the first moment of the M over EI diagram about point B. Therefore, we can rewrite it this way, where x bar is the distance from the center of the M over EI diagram to point B. This equation represents the second moment area theorem. Geometrically speaking, it states that the distance between the two tangent lines, measured at B, is equal to the area under the M over EI diagram times the distance from the center of the diagram to point B. Let us determine the vertical deflection of our cantilever beam using the second moment area theorem. Here is the M over EI diagram for the beam. Here is the elastic curve, and here are tangent lines at A and B. Note that this height is the same as the vertical deflection of the beam at B. Hence, the deflection can be determined by taking the moment of the area under the M/EI diagram about B like this. Therefore, the deflection is 24/EI. Generally speaking, the second moment area theorem enables us to determine both slope and deflection in beams, whereas the first moment area theorem can be used for calculating slopes only. Now it is your turn. Use the moment area method to solve the following problems.